atomic or hybrid atomic orbitals. The whole point of hybrid atomic orbitals is to answer, or to address the problem, I should say, answer the question of geometry. You see, I'm trying to overlap atomic orbitals to make covalent bonds. The trouble is, atomic orbitals come in S's and P's and D's and F's, and those are 1, 2, 4, and 8 lobed type orbitals that don't exactly lend themselves very well to things like a tetrahedral or a trigonal bipyramidal, or those geometries, those electron geometries that we've seen. And so to get around this and to explain it, one approach is to use hybrid orbitals. The idea of hybrid orbitals is that since the electrons are waves, they're not like stuck in their shape around a single maybe atom. Yeah, I've got an S shape or a P or a D, right? But when I bring in another atom and I start overlapping and interacting those electrons, they are free to adapt to that new environment and to change the shape of their waves. They're not going to stay spherical for an S or a dumbbell shape for a P. They're going to change and adapt to the shape. And to recognize that, then we can say, well, what are they adapting? How are they going to change? Well, they're going to do so to adapt to the new geometry of the molecule with its new bonds. All right, so we call these hybrid orbitals. One way to think about it is I'm bringing in the atomic orbitals, I'm massaging them, I'm just squeezing them, I'm changing the shape then, I'm mixing them together, if you will, to get hybrid orbitals with the correct geometries. Now it makes sense, I can't create or destroy matter, I can't make electrons or destroy them, and so the number of orbitals that I need and the normal number of orbitals that I used to satisfy that need have to be the same. In other words, think about a linear type of a molecule. I've got a direction to the left and to the right. Going to the left, I'm going to have a bond, which has 2 electrons, so that must be one orbital. Remember, an orbital could be a spin up and a spin down. It can hold 2 electrons. So that bond could be satisfied with an orbital of the right geometry going to the left. Similarly, I could have one going to the right. I think it's quite clear for a linear molecule I'm going to need 2 types of orbitals with the correct geometry, which means I have to take that central atom and use 2 of its atomic orbitals, massage them, bend them, squeeze them, hybridize them together to get the correct geometry orbitals. All right. So that's kind of the overall picture, and we're going to go through the steps here that lead to that one by one. All right. Let's see the rules or ideas behind these atomic orbitals, these hybrid orbitals, excuse me. The book lists 6 of these things to consider. Number 1, only in covalent bonds. We don't need them in ionic. Right? With ionic, we're not sharing the electrons. We're not overlapping orbitals. We're literally giving an electron from one atom to the other. So unnecessary there. But when we're sharing and overlapping, yeah, that's when we need to talk about the geometries and the hybridization of these orbitals. And so, yeah, we only need these in covalent bonds. Number 2, we get new shapes and orientations. I've highlighted this because not only do we get the new shapes and orientations, but that's the whole point of doing this in the first place. That's why we're doing hybrids, is to accommodate the correct shapes and orientations that these electrons need to be in. Number 3, I already talked about this. The number of hybrid orbitals that you get out has to equal the number of atomic orbitals that you put in. You can't destroy or create, so what goes in equals what comes out. It has to be the same number. Again, we'll see that in just a second. Number 4, a set of new hybrid orbitals all have the same shape and energy. So if I get new hybrid orbitals that match a trigonal planar geometry, 3 different ways, right, 120 degrees between them, they're all going to have the same energy, just like the p orbitals all have the same, or the d orbitals, they have the same, right? Same idea here. We'll get 3 orbitals which accommodate a trigonal planar geometry that are all going to have the same energy. And they're going to have the same shape too. They're basically going to be a big lobe pointed out in the direction of one of those legs of the trigonal planar molecule. The other 2, same shape, just oriented differently. One points this way, the next one points at 120, the third one at 120 degrees from that. All right, so same energy, same shape, just the orientations will be different. Number 5, the type of hybrids depend on the valence shell electron pair repulsion electron geometry. Not the molecular, but the electron geometry. See, these new shapes, these new atomic hybrid orbitals that we're creating have to accommodate both lone pairs and bonded pairs, not just the bonded. And so what we need to do is look at the electron geometry, and that will give us a clue as to what type of hybrid orbitals we need to accommodate that geometry. And finally, number 6, hybrid orbitals overlap to form sigma bonds only. Atomic orbitals overlap to form both sigma and pi bonds, and that will be clear when we talk about the actual creation of the bonds once we get our hybrids and the creation of multiple bonds in the next section. Alright, so how does this work? A lot of background here, but it's not going to make much sense until we actually do a few examples. To create the hybrid orbitals, it's actually a mathematical rigor to it and theory in which what we're doing is we're doing linear combinations of the wave functions of the atomic orbitals. Linear combinations. So 25% of this one, 75% of that one, add those functions together. It's that sort of an idea, linear combinations. In simple terms, we're essentially adding the atomic orbitals together in different percentages, and those atomic orbitals being sP's, d's, and f's in their various orientations and sizes, together to produce these hybrid orbitals that again will give us the correct shape and geometry that were required. And there's a nice little table here in the book, and here I've summarized it, which I think will start to clarify things. Let's say I've got a linear molecule. Down here, linear molecule, it's got to go left and right, something like here. Alright, so my nucleus is right there in the middle, and I've got to go to the left and to the right at 180 degrees. Again, this would be one hybrid orbital pointing to the left. This would be one pointing to the right. For my two bonds going out that I don't have any lone pairs, I have nothing else. I mean, this is linear, only two things are coming off. So I need two orbitals. How can I get two hybridized orbitals? Well, I can do that by using two atomic orbitals and squishing them and mashing them together and changing their shapes. When I do this, I always go for the simplest, and then I build up from there. And so the first orbital in any energy level that I need to consider, the s. Remember the Aufbau principle, that's the first electron position or destination, if you will, that it goes into when I'm filling the correct order of electrons. And so I would take an s orbital, that's one of them. Now there's only one s orbital, so now what's next is one of the p orbitals. Now there are three to choose from. I only need one of them. Right? So I'm going to take one of those p's. I got an s and a p, and that's what they're showing right there. An s and a p, they get smushed together, rearranged to give me these hybrid orbitals that point left and right. So instead of the spherical s and the dumbbell-shaped p, I'm getting the atomic orbitals, hybrid orbitals, excuse me, with the correct geometries. And again, because I had two directions, I needed two orbitals, and so this is called an sp hybrid. An sp hybrid. And that's what I've got here, the number of electron regions for an sp hybrid, two of them, which is what you require for a linear shape. A trigonal planar, well, I've got three directions, so I'm going to need three orbitals. So I grab the s, and I grab two of the p's, maybe the px and the py. The pz orbital, left over, don't use it. It's just going to hang out there, and it's still going to remain on that atom, but it's just not going to be used. Right? So here, again, trigonal planar, I need three of them, so I grab an s and two p's. That's going to be called an sp2 hybrid. Perfect for a trigonal planar type of an arrangement. And I can go up right through these five basic shapes that we've learned before. Tetrahedral, I need four different directions, so four orbitals. I'm going to grab the s and all three of the p's, so four atomic orbitals go in. Four of these hybrid orbitals come out that I call sp3s. There are four of them. They all point in different directions, the directions of a tetrahedral. Right? For five things coming off, trigonal bipyramidal, I'm going to need sp3 and, well, what's next? D, the d orbitals. Right? Of course, this has to be in the third energy level to do this kind of a hybrid, where these ones could exist in the second energy level. Third energy level is the first time I see a d, so if I'm going to do this type of hybrid, I better be using at least a three-level atom. But anyway, five different directions, five orbitals, sp3d is the hybridization. And finally, for octahedral, six different directions, so I need six orbitals, so sp3d2 hybrids. Again, I would get six of those, all pointing in the correct directions for an octahedral. So you see, the type of hybrids I'm forming is just tied very closely. Indeed, it's directed by the geometry, the electron geometry of the molecule that I need. Right, so, for example, let's do SO4 2-, the sulfate ion. And let's find out what type of hybridization that sulfur atom, the central atom, needs to be in to do this. Alright, we need to go through and make our Lewis electron dot structure so we can get a sense of what electrons there are and what needs to be shared and what lone pairs and all that kind of stuff. I need my electron geometry, in other words. So sulfur has 6 electrons, and I got my 4 oxygens. They each have 6 too, so that's 24. Then I've got my 2 negative charge, that's an additional 2. Add that together, 32 total electrons. Alright, for 32 total electrons, I'm going to put my sulfur in the middle. Oxygen, 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 oxygen. Let's give everything an octet. So I go around like this. And I say, how many electrons have I used? 2, 4, 6, 8. Another 8, another 8, and then that's 32. So looks pretty good. There's my 32 electrons. Of course, if I looked at formal charges here, I would recognize that sulfur actually has a +2 formal charge, and each one of these oxygens has a -1. And I could actually do a little bit better than that by simply moving these lone pairs of 2 of these anyway down to make a double bond here and a double bond like that. That gives a formal charge of 0, 0, 0, and then a -1 in this oxygen and a -1 in that oxygen. So that's a slightly better one. Right. Either way, you look at that central sulfur, and what's the electron geometry? Well, I've got a double bond, a single, and a single. No lone pairs at all. So there's 4 things coming off of that. 4 things I know has an electron shape of a tetrahedral, and a tetrahedral requires an sp3 hybridization. So it's just that simple. Sulfur in that molecule has an sp3 hybrid. Let's try one more. Selenium tetrafluoride. So selenium, let's look at the periodic table for that one. Selenium is right down here underneath sulfur, so that has 6 valence electrons. So Fe has its 6, and I've got 4 fluorines. Each one of those are 7, so that's 28. No charge on this one, so that's 34 total electrons. So if I try to arrange this symmetrically, I'll have my selenium, fluorides or fluorines all the way around. Give everything an octet in the usual way. Count the electrons that I've used. 8, 8, 8, 8. That's 32. Whoops, I needed 34. So I put my extra lone pair on that central atom. There we go. I've used 34 electrons. Everything has a tetrahedral except for that central selenium, which has actually 10 electrons, but it's okay. It's a large atom. It can accommodate 10. If I look at the formal charges, each one of these fluorines are going to have 0. They own 7. They usually have 7. And the selenium owns 1, 2, 3, 4, 5, 6. It usually owns 6. So 0 all over for the formal charges. So this looks like the correct Lewis electron dot structure. Alright, so what about the hybridization? Well, let's look at that central atom. There are 5 things coming off of that, right? 4 single bonds and then this lone pair. So 5 things coming off. I know the overall electron geometry is going to be trigonal bipyramidal for 5 things. 5 things going off. I need 5 atomic orbitals to mix together and hybridize. So that's going to be an sp3d. That's a grand total of 5 right there, right? 1 s, 3 p's, and 1 d. And so sp3d is the hybridization of the selenium in that molecule.